Welcome to the JPSS and GOES Fire Monitoring Capabilities teletraining session. My name is Gerald Torres and we'll be leading this teletraining session today. Note that this is the September 2021 update, and so let's get started. First of all, I have some learning objectives for users for this teletraining session. First of all, I want users to be able to reinforce their understanding of JPSS and GOES and their capabilities. I would like users to become more acquainted with JPSS and GOES datasets and their applications for nighttime and daytime fire detection. Also, I'd like users to be able to recognize differences between VIIRS and GOES IR, temporal and also spatial resolutions, and along with identifying HRRR smoke, satellite-derived soundings, and GOES quantitative fire product applications. In addition to that, with all the datasets that I will highlight here in this teletraining session, I would also like users to be able to acquire satellite training materials, which I will provide at the end of the session. So first of all, just a few thoughts and recap of the new satellites and their capabilities. First of all, the last few years we've had these new satellites that have launched and are currently in orbit providing satellite imagery and products for our users. First of all, you have your Joint Polar Satellite System, or JPSS, that encapsulates both the SUMI National Polar Orbiting Partnership satellite along with NOAA 20. Now there's analogous instrumentation on board each of those satellites. The ones of focus here are the VIIRS and ATMS and also CRIS instruments. With the VIIRS instrument, you have 22 spectral bands at high spatial resolution, and then you also have your ATMS and CRIS, which you can be utilized to provide your temperature and moisture profiles via satellite-derived soundings or into the blended products, and then also integrated into your numerical weather prediction models. In addition to JPSS, you also have your GOES satellites, GOES 16, GOES 17, that have the ABI on board. Each of those satellites that have 16 spectral bands at high spatial resolution, and also providing a frequent temporal refresh rate as well. Now the question becomes, with all these satellites and also datasets for users, how can users employ both JPSS and GOES satellites with respect to fire monitoring? So this teletraining session will cover the utility of JPSS and GOES imagery and how they can complement each other for fire monitoring. And then also note that this teletraining session will highlight a variety of fire case examples throughout the session as well. So let's get right into it. We'll start from the GOES perspective, from the nighttime fire detection aspect. Here's an example from the 243 command fire out there in central Washington. Here's a 4-panel animation here, highlighting before the fire initiated, then to fire initiation, and then the evolution thereafter. Within this 4-panel here, users can see and observe the fire hotspots and observe the fire in different ways. Of course, you have your standard 3.9 micron in the top left, where you can observe the thermal signature there of the fire exhibiting warm brightness temperatures. In the top right, you have your fire temperature RGB that you can utilize in a qualitative manner to infer your fire intensity, and which I will highlight a little bit more in the next slide. And then in contrast, in the bottom left and also bottom right, we have our microphysical products, which are usually used by users to differentiate between your ice and liquid water clouds. But note that you can also observe your fires as well within these products because they also employ the 3.9 micron channel with the brightness temperature difference here for the night fog difference product here, and then your nighttime microphysics RGB, which employs that same brightness temperature difference within the green spectra. So within the night fog difference product here, you can observe your fire hotspots in black pixels, and then in contrast, you have your nighttime microphysics RGB that can be observed in a darker magenta colors. Now, as we transition to the daytime for this same fire event, you can observe the fires in a few different ways as well. As I mentioned, you have that fire temperature RGB that users can employ in a qualitative manner to infer your fire intensity. So pixels will transition from red to orange to white, red to orange to yellow to white pixels. Red pixels indicate your cooler fires, where yellow and white pixels indicate the most intense fires. So you can see within this fire event that it it appears intense just east of Beverly, or the town of Beverly, and as it moves eastward, the fire appears to be more intense on the eastern flank of that fire. Now, in contrast to that RGB, we also have the Dayland Cloud Fire RGB in the top right there, which this RGB is sensitive to fire smoke, which you can see in the bluish gray here, and then also vegetation health in regards to burn scars for hydrological applications. Now, I'll get a little bit more into that near the end of the teletraining session, just highlighting a few examples then. And of course, you have your standard spectral channels, you have your standard visible, where you can observe your fire smoke here, and then also your standard 3.9 micron to observe your fire hotspots as well. Now, I'll transition here to some of the polar orbiting products that users can employ for fire monitoring, and that they can utilize and complement to your geostationary datasets. The first one here is the VIIRS Near Constant Contrast product, or NCC product, that is in AWIPS for users. The NCC is a derived product of the day-night band that users may be aware of, which illuminates your atmospheric features via reflected moonlight, and also senses emitted lights during the nighttime. It's also known as nighttime visible imagery. And what you can see here is emitted lights from your cities and or towns along I-70 here in western Colorado. But most importantly, you can see the emitted lights from the Pine Gulch fire that occurred just north of the town of Grand Junction, Colorado here. Now, in addition to being able to observe emitted lights from fires, you can also observe nighttime fire smoke. And here's an example out here in western Oregon back in 2020. You can observe your fire smoke with the NCC product. Now, in combination with the NCC, you can also compare it to your 3.7 micron channel to observe your fire hotspots. And the point of this is to correlate which emitted lights are associated with the fire compared to emitted lights that are associated with the cities and or towns. So what you can see here with the 3.7, you can observe your fire hotspots in the, within those darker and also black pixels here that kind of outline the fire perimeters, and you can see the corresponding emitted light that's being produced from those fires. So you can infer that these particular areas by my cursor are associated with, the emitted lights are associated with the fires. Now, in contrast, along the Interstate 5 corridor here and also westward as well, you can see emitted lights here, but you don't see a corresponding thermal signature. So that would infer to me that these are emitted lights from cities and or towns. In addition to this, you also have the VIIRS Active Fire product. Now, this product can be utilized during the day and or nights. Now, in AWIPS for users, it's at 750 meter resolution at the moment. However, there are plans to try to get the I-band imagery, the higher resolution, that 375 meter, into AWIPS, hopefully during this fall 2021, or at least before the end of the calendar year 2021. This particular product has three main display outputs as fire location, fire radiative power, which is also known as fire intensity, expressed in megawatts or MW, and then also has the fire detection confidence from 0 to 100%. So essentially the percentage that a fire exists within a pixel. And here's just an example of the VIIRS Active Fire overlaid onto the GHOST 17 visible imagery, where you can see the fire smoke here over Lake Tahoe near the California-Nevada state line. And what you're seeing here is the fire points from the Caldor fire in California that occurred within the last month or so here. And you could also see the varying levels of intensities that are being observed by the VIIRS Active Fire product here, where it's color-coded here, so the yellow dots indicate the less intense fires, and as the colors transition from yellows to oranges, then oranges to red to dark red, the more red and dark red it becomes, the more intense the fire is. So you can see how the fire is more intense at the moment from the swath in the northern periphery of the fire and also the northeastern periphery of the fire. And then also some data points are intense on the southeastern periphery of that fire as well. And then here's just an example sample that highlighting some fires out there in Northern California, where the cursor is over this orange dot here, which then samples the timestamp of the polar orbiting overpass, which comes from NOAA 20, and also highlights the fire detection confidence, which at this point is at 92% confidence that it's a fire. and then also has your fire rated of power, which is at approximately 68 megawatts there. In addition to the VIIRS Active Fire, we also have the VIIRS Fire RGBs that users can employ in a qualitative manner, and you can also be able to observe your fire smoke components with the VIIRS Dayland Cloud Fire RGB here, and then also some of the PyroQ that are being observed by the Dixie Fire. And note that with this RGB, as it's similar to the GOES version, you also can be able to observe your burn scars as well. So you can see some of the older burn scars from the Dixie Fire, but then also from other fires here in the southern portion of the southern and also southeastern portion of the scene as well. And of course, you could also see your fire smoke component. In addition to the VIIRS Dayland Cloud Fire RGB, you also have your VIIRS Fire Temperature RGB at the same timestamp of the fire, in which then you could see the areas that are most intense are indicated by the yellow and white pixels, which are on the northern periphery and northeastern periphery of the fire at this particular timestamp as well. Also, I wanted to highlight to users just some of the differences in regards to the ABI infrared spectral channel compared to VIIRS, and how they can be utilized together for fire monitoring. Here's just an example, just revisiting the 243 command fire in central Washington at this particular timestamp. Within the white ellipse, there is a fire, and from the GOES perspective, of course it has that higher temporal refresh rate. However, the spatial resolution is not as fine as the polar orbiting VIIRS datasets. So it's a little bit more challenging to see where the fire is. However, you have a higher temporal refresh rate with geostationary datasets. Now, in contrast, for the VIIRS perspective, your datasets are not as timely. However, you have a finer spatial resolution, so you can see the fine details of the fire, and then also you could also see the fine details of the river to the west here, exhibited by the colder brightness temperatures as well. But the point is that you can utilize both datasets together for fire monitoring, and just know the limitations of both datasets. And then here's just a table that kind of encapsulates some of the characteristics, and whether they be similarities and or differences between the spatial resolution, temporal resolution, AWIPS data latency, or the time of the satellite overpass to when that dataset is seen in your AWIPS system, and which they can vary here. From the polar orbiting perspective here, that data latency can be an hour to hour and a half, but if you're utilizing your direct broadcast data sets, it's at approximately 30 minutes or so. And then the last characteristic I wanted to highlight is that is the differences in your saturation temperature that leads to fold over. With your GOES data sets spectral channel here, you have a higher saturation temperature compared to your VIIRS data sets. So if you have a very intense fire, you'll see that your VIIRS datasets saturate faster compared to your GOES. So just be aware of that, whether that be you're observing your fires via the individual spectral channels or utilizing RGBs or products that employ these spectral channels individually as well. In addition to that, I also wanted to highlight just a few other products before I come to a close. I also wanted to highlight the HRRR Smoke model, which is a fan favorite for fire monitoring, especially for smoke monitoring as well. And then here's just a few examples out there in the western CONUS of the near-surface smoke, and also the vertically integrated smoke products as well, where they simulate your fire emissions, plume rise, and also your smoke distribution of those fires. That can be helpful for visibility concerns and air quality and human health aspects as well. Note, these datasets are available in AWIPS and also online. There's a link there at the bottom left. And also be aware of the vertical cross-section capability that is also available, where you can observe your simulated fire smoke concentrations with height. Here's an example of the simulations from the Cameron Peak fire, and also I believe the East Troublesome fire out there in northern Colorado back in October of 2020, and you can observe those smoke concentrations with height over complex terrain. Also, I wanted to highlight the capabilities of satellite-derived soundings that users can employ in their AWIP system. You have your NuCAPS datasets that are essentially temperature and moisture retrievals that come in satellite SWATs, whether that be in green, yellow, and red dots. Green dots indicate good quality soundings here. Now these NuCAPS soundings are useful, especially in data sparse regions or when RAOB observations are limited or non-existent. And here's just the gridded NuCAPS data set, which you can observe the TPW values in a plan view capability over western Colorado during the time of the Pine Gulch fire out there in western Colorado, denoted by the star there. And note that I highlighted both a NuCAPS sounding compared to the local RAOB from Grand Junction. And if you compare those two, you can see the similarities and differences. Note that the timestamp difference between the two are about 4 hours apart, but note that with NuCAPS you can utilize them, especially out there in the western CONUS, and observe near fires as well, especially in clear sky environments, to observe your upper level atmospheric temperature and moisture profiles, and then also how the NuCAPS soundings compare to your RAOB. And, of course, with the RAOB, it's a more finer measurement compared to the NuCAPS volumetric measurements from satellites. But now, see just the comparisons there. It's a very dry boundary layer that is being observed near this fire, and note that the RAOB captures the low level inversion, which the NuCAPS struggles with a little bit. But note that there is 4 hours difference between these observations. But just know that NuCAPS capabilities in assessing the atmospheric thermal and moisture components. And then lastly, before I come to a close, I wanted to highlight some of the quantitative products from your GOES data sets. And this is just highlighting your fire temperature, your fire power, and also your fire area data sets that users can employ. Fire temperature is expressed in Kelvin in your top left, fire power in megawatts in top right, and also your fire area in square meters in your bottom left. And then this is just an example of a small fire out there in Florida, and also a sample there of being able to observe those fires as well. But also note that there also exists in AWIPS for users. It also includes a processing information in the form of a mask, so you can differentiate if a particular fire that you're observing is a process fire, or if the pixels are saturated, or if it's cloudy, or clouds are being detected, and then also varying levels of the probability of a fire being existing within that particular area. So just note of the fire mass that is available for you as well. And as I come to a close, here's just a summary slide highlighting a lot of your training resources. Essentially, all the products, spectral channels, and RGBs I highlighted today. There are corresponding satellite training materials that users can employ and use to assist them to help for interpretation. And but essentially, the overall hope is for users to be able to employ these data sets to assist them in operational management decisions, and also IDSS to help protect lives and property across the U.S. And I'll come to a close here. If you have any questions, you can email me at your earliest convenience there. And I leave you with some burn scar imagery that can be helpful for users to diagnose areas for future potential hydrological applications, such as flash flooding that may occur in their respective areas. Here's an example from the GOES perspective in the right, from the Woodbury fire, of the burn scars that exist there, and then also a more recent example from the VIIRS Dayland Cloud Fire RGB perspective, observing burn scars earlier this year in 2021, observing the Mullen Fire burn scar that straddled the Colorado-Wyoming border, and then also your East Troublesome and also your Cameron Peak burn scars as well. So with that, I thank you for your time and attending this teletraining sessions. But as I mentioned before, if you have any questions, don't hesitate to email me. And thank you for your time.